Hi folks, hi, time for another episode on the BIVBlog, Benedict's IT video blog. And today it's back to teaching the turtle to dance. In case you don't understand what this means, take a look here. It's from a long time ago. And in case you wonder where I got this from Stockholm, from the last Cryptech meeting I attended some time ago. And what I want to talk about today is how to filter ICMP with IPv6. Now, as you've probably heard over and over, ICMP is evil and it has to be filtered away and blocked and everything. And with IPv6, it's 6 times as evil. Stands to reason, right? So if we can't filter all of it, well, something is broken. Well, if we filter all of it, something is going to be broken, which is IPv6, because it's not going to work. And well, because of that, then we can't possibly use IPv6 because we can't make it secure. Despite the fact that these days we even get IPv6 NAT. Yeah, and anyway, back in those old days when you just had 2 tin cans and some bit of string, everything was much better anyway, right? I guess you've all heard things like that in the past, and well, yeah, sure, right. Go back on your trees. And if you want to do IPv6, maybe just because we don't have another choice, we actually have to get more sensitive about this. And there are a couple of things you want to keep in mind when it comes to filtering IPv6. First off, every packet filter is a potential reason for loss of service. Packet filters are susceptible to misconfiguration. Oh, really? They are susceptible to being a bottleneck, performance bottleneck. They are susceptible to possibly denial of service attacks. And generally, they can be quite a pain in the ass. Let's face it. On the other hand, sometimes, or more often than not, the only defense we have is some sort of defense at depth. So we need multiple layers of security measurements, and then packet filters are simply something we can't do without. Right. So we don't want to just plaster our networks with packet filters, but want to put them where they actually make sense. And another issue we want to keep in mind is that packet filters are frequently not as smart and powerful as we might like them to be. One of the biggest issues I have with a lot of packet filters I've been taking a look at over the years is that they are, well, I'm not even going to say limited, but they simply can't associate ICMP packets with existing connection states, despite the fact that a lot of ICMP packets can only occur in the context of some sort of connection. And that's annoying. And it gets even worse when it comes to multicast, because that's where things get really tricky to decide where is the associated state. The reason why this is frequently limited in capability is that packet filters, which do this in software, are frequently susceptible to denial of service attacks. Then, if you have too powerful filter mechanisms, which are too CPU intensive, you risk denial of service attacks. Other reason is that implementers haven't got as far as they should, and things get really ugly when you do this in hardware. And once you reach certain sizes, you actually have to do filtering in hardware, and that's a real ugly topic. Another issue we have is ICMP extension headers, or sorry, IPv6 and tech extension headers, option headers, which are frequently impossible to be filtered in a particular precise way. A lot of times it's allow them or don't allow them at all, and not by different extension header types and whatnot. And what's also troublesome is the issues with tunnelings. with tunneled packets. I don't think I've seen any packet filter that can actually look in the inner packet in a tunnel packet. So IPv6 is broken, right? Yeah, but problem is there's a problem with the perception, because IPv4 is just as broken, but we've been using it for so long we don't notice any longer. And with IPv6, which is new, we take a much closer look, realize, okay, we've got these and these and these problems, and whoa, and we completely ignore that with IPv6. No, it's not better, not at all. It's, in a number of ways, it's actually much worse. So that's basically our situation. First thing we have to do if we want to filter ICMPv6 is figure out what ICMP types and codes are there. And the obvious place to go and look for is, well, no, not IANA, Wikipedia. You go here and take a look at that, and there you find a link to IANA, the Internet Assigned Numbers Authority, who have the definite list of assigned ICMPv6 types and codes and whatnot, which is here. Good. So let's take a look. There are a number of ICMP types. Most of these should be kind of familiar, and then there's some more, and there's some more obscure ones in there, like ICMP node information stuff and inverse neighbor discovery. And then there's some more, well, there's some mobile IPv6, but I've got no idea what certification path stuff is. And I've taken a look at CMOBI and decided this is not something I want to touch. And yeah, there's even more. And I've got no idea what a duplicate address request, duplicate address confirmation is. Never seen that. Should probably read the RFC. But anyway, with round about 60 ICMP types, and I don't even list ICMP codes used for different things here, we have a bit of a problem. And we should think first how we want to tackle this. First question is, do we want to do blacklisting or whitelisting? And a lot of times I ask this question in trainings. The immediate answer is there's only one way to do it, and that's whitelisting. I'm not going to let anything through that I haven't specifically checked. In a number of high security environments, that reasoning is plausible. But if you work, for example, for one of those mass consumer grade ISPs, that's not what you want to do. In that case, you want to do blacklisting and just filter whatever you know is causing trouble. Why is that? Because if your filtering breaks something for a customer, you're pretty likely going to lose that customer, or at least cause some serious expenses in your support and get you a bad reputation. I've got internet access there and so doesn't work, but with a friend of mine it actually does work, and my access is broken. My ISP screwed up. Not a good thing for business. So you want to figure out what you want to do. And by the way, if you work for a business customer oriented ISP where filtering and security things are part of your job, things look completely different again. So you want to figure that out. And sometimes you actually have to talk to management about what to do or not. Second thing you want to do is sort out whatever you're pretty confident you don't need. If you have 60 ICMP types, it doesn't make much sense to figure out, okay, what is CMOBI and do I actually use it? No. Just filter it and put a note in there. This is for so-and-so and we currently don't use it. And if you use Cisco for access lists for packet filtering, where you can't have any proper comments, well, document it elsewhere. Next thing you want to do is you want to reorder them, because, for example, multicast listener discovery is not in one contiguous block of ICMP type numbers. And ordering things like this just makes it easier to understand what you've done like a year or two ago. And while you do that, aggregate them. There are 4 different ICMP types for MLD, so keep them together. There are 2 for ping, echo request, echo reply, and whatnot. And then it's time to get your hands dirty. And what I use is sort of like a cardboard note, and it looks like this. There's a description or name, whatever you need to understand what you're doing there. If you're familiar enough with ICMP, you just use the names. The ICMP types and codes, from where to where these packets are being sent, and then things get interesting. Are these packets going to be forwarded or not? A lot of ICMP types don't get forwarded, and especially if you use Linux for a packet filter, which has this beautiful little thing with a separate forward chain. This is really important. A lot of ICMP types don't get forwarded, and you shouldn't allow them on a router to be forwarded. Then there's this thing about hop limits. For example, if we use an ICMP redirect, that's not going to be forwarded anyway. And to prevent abuse even without a packet filter, the standard approach, or what's actually done according to the specs, is these have to be sent with a hop limit of 255. And if you receive such a packet with a hop limit other than 255, you know it has been forwarded somewhere, and this is simply wrong. So you just discard it. This can be quite helpful to figure out if there is something going wrong on your network, if there's some sort of stupid attack going on. Another thing that's really interesting and troublesome is this sort of ICMP type associated with some sort of state, or does it create some state, or is it stateless? Can be quite useful once implementations actually get a bit more powerful on that, in that respect. And despite the fact that these days implementations are pretty stupid with regard to this, it helps to understand if they are related to a state or not. And of course you want to know more precisely what they're used for and in what context and what special things are there. And yes, I've done a couple of these slides, and they are available in the on the BIVBlog. I make the entire presentation available there. We have to take a look at these things, and it basically works like this. First off, we start with multicast listener discovery. Why? Well, why not? So here it is. So first thing we have is multicast listener query, ICMP type under 30, and it's only sent from link local multicast to either the all node link local multicast address or unicast. Both of them possible. They're not forwarded. Unfortunately, they don't use this hop limit 255 trick because multicast listener discovery is older than the idea to actually do it like that. They are not stateful. Well, you might actually figure out where the state is, but I don't think you can do that at line speed and a packet filter. They are important when you use multicast listener discovery on MLD capable switches, or if you use multicast routing. They have a router alert option, but the important thing here is that these MLD capable switches are a way to really screw things up in the long run. Because if you only have some cheap ass switches or some old ones that only do IGMP for IPv4 but they don't do MLD snooping, then you can filter these and things will work. until you replace that switch. And all of a sudden, the brand spanking new switch, which is supposed to be IPv6 capable, doesn't work. And by the time you figure out what actually happened, it's going to be really embarrassing. So when you use MLD, you want to allow MLD no matter what, even if your switches these days might not yet support it. Or don't do MLD snooping. Similar thing if you try to set up multicast routing and things don't work and eventually you figure out, oops, I screwed up in the packet filters. So my advice is allow these. There might be exceptions if you have very, very hostile link layer networks. So if you have guest networks, conference networks, that sort of stuff, you might put a bit more thought in there. Similar thing for MLD version 2 multicast listener reports. Different addresses where things go to, but otherwise pretty much the same story. These are details. I'm not going to explain every single one of them in full detail because that would be a long video. And similar thing, version 1 multicast listener report. The addresses again are different. And then there's multicast listener done. Yet another address. It goes to all routers, link local multicast address. And in theory, these could be stateful if there's ever any implementation that actually deals with this sort of state. Okay, next, there are a couple multicast packets you really, a couple ICMP packets you really shouldn't filter. That's packet too big, because if you filter packet too big, fragmentation will break. That can work in networks that are designed in such a way that you won't have fragmentation, basically have the same MTU all over the place. But if you screw that up, troubleshooting will be really, really painful, and not just for you, but for other people as well, in all likelihood, and you'll really make enemies doing this. This is one of those things to really annoy people, because if you filter on your router and the setup looks accordingly, it'll appear to everybody like that the problem is somewhere completely else. And tracking a packet filter that's throwing away packet too bigs is really, really difficult if you don't have access to all the machines involved. And this is exceedingly important if you're an ISP or provide network services, for example, in a data center. So by all means, let these through unless you have very specific reasons to filter. Another thing, ICMP redirects. Now, the good thing is that you can design your networks in such a way that redirects don't occur. Basically means don't have multiple routers in your network that route to different places when there are hosts involved. Simplified. In theory, it could be associated with some state, but I wouldn't expect any implementation to do that anywhere in the near or not so near future. If you're absolutely sure they can't occur, then you might want to filter them, or actually filter them and log them because something really fishy is going on. Good news is these shouldn't be forwarded, so you don't let them through in a forwarding setup. So these are important. Then there's destination unreachable, one of my favorites. Why is that? Because first off, there are 8 different types, and I haven't memorized all of them either. If you block destination unreachable, they lead to a situation where a connection waits up to 3 minutes for timeout. And I've seen people filter destination unreachables on IPv4. And if that means that your users can't access certain websites, or they are tremendously slow to access, it's a problem with that website, right? They can access them from home, but not from your network because you're secure. And it's actually kind of difficult to decide, for at least for an end user, that there's something wrong with your network. With IPv6, you don't have just round-robin DNS, which used to cause these problems with the IPv4, but you have much more of a chance that they are both IPv4 and IPv6 addresses in the DNS, and there are possibly even multiple IPv6 addresses. That's n times 3 minutes waiting. Be really careful when you filter these. Nasty thing about them is they need to be forwarded. Good thing is they could be associated with a state of a packet filter that could actually deal with that. Final one, TTL exceeded, time exceeded, hop limit exceeded. You find different names in different RFCs. They should be stateful. They need to be forwarded. And if you filter these and you use dynamic routing, or somebody else along the path uses dynamic routing, all sorts of funny things happen. If you filter these, troubleshooting will be, once again, a real pain in the ass. So don't filter them unless you really, really, really know what you're doing, and only do this in a closed network. There is another time exceeded, fragment reassembly time exceeded, which is caused by packet filters that try to reassemble, or packet filters, or end targets that try to reassemble fragments and run into a timeout. They should be stateful again. They need to be forwarded, and otherwise they should be treated basically like a packet too big, because similar problem. Then there's the general protection fault of IPv6, the parameter problem. It's used for all sorts of funny stuff, and it needs to be forwarded. It should be stateful, but if you see these, there's some serious problem. They're essential for troubleshooting. Yes, they should be rare, and for setups I'd consider normal, for normal definition of normal or typical. I would let them pass, but I'd log them. I'd make sure that I see if they occur, because it means there's something wrong somewhere. Okay, so then there's the stuff that's real fun, neighbor discovery. Neighbor discovery, once again, doesn't get forwarded. It's not stateful, or neighbor solicitation is not stateful. You might reason that it creates a new state, but depends on what you want to do, really. In theory, you can filter these, or deny these, block these, but then you have to configure your neighbor cache statically. And I've only had only know of one case where people actually were doing this with the IPv4, with the IPv4 equivalent, which was the ARP cache. Ultra-high security setup where communication was supposed to be only going one way. They cut the other pair of wires in Ethernet and whatnot. And that was actually in a military context. No, I wasn't involved in that project myself, but it was, I've heard about it at some sort of conference. What's important here is that IPv4 focused people will frequently complain about this, and this it's complicated and whatnot, and with the IPv4 it all works automatically. Yeah, because with the IPv4 you need ARP, which is a lower layer protocol, which is something halfway between layer 2 and layer 3, and people don't filter it and just let it through. And filtering ARP on IPv4 is actually quite quite painful with a lot of packet filter implementations. With IPv6 you can filter, you should filter, and okay. Neighbor advertisement should be stateful, yes, and you need this for duplicate address detection, neighbor discovery, blah 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 blah, same thing as before. Another thing, and you can actually turn that off if you know you don't need it, is auto configuration. Stateless address auto configuration, that is. If you have networks where you know there's only statically configured hosts and or routers, and you do, for example, a backbone network where there are only routers connected to anyway, you can filter these. Sure, fine, why not? Otherwise, leave them open. And if you have a network where you don't have any auto configuration right now, but might actually add it in the future, put a comment in place. Similar thing with router advertisements, same story. And then there's ping, echo request, echo reply. Couple interesting things. First off, with IPv4, it's very convenient to ping the all node or all router link local multicast address to see what else is in the network. Pinging multicast addresses is something a lot of people think is weird. And with IPv4, there was this Murphy attacks a long time ago where people pinged a broadcast address somewhere else and all machines answered at the same time, and used a fake source address for your echo request and used that for the denial of service attack against somebody else and all this sort of stuff. With IPv6, this is decidedly different. What you want to filter, you want to think about yourself. When it comes to unicast ping, yes, there are probably situations where you want to filter it, but in the majority of cases that I've seen, filtering them is a bad idea because it makes monitoring and troubleshooting much more difficult, and that means you'll have longer downtimes when things go wrong. So think about that. Same with echo reply, and that's the basics, the things I consider really, really important. So, in summary, because you're always supposed to do a summary, right? First off, if you filter all ICMP for IPv6, nothing's going to work, because you need at least neighbor discovery. The link local scope and this hop limit 255 trick save a lot of problems. It's much easier to decide which ICMP packets are only used within the local subnets, which don't need to be forwarded. That can be quite useful. Connection tracking still has to catch up. And multicast, once people start seriously using it, will actually make things slightly more complicated. So that's pretty much all there is about this. Well, there is much more, but if you want to take a closer look, there are two books I'd like to recommend. First one is Sylvia Hagen's IPv6 Essentials, and mid last year the third edition became available. If you want to figure out what exactly these are for and want to understand the protocols in detail, that's, well, kind of the standard reference, except for the RFCs, which are a bit more painful to read. And this stuff is really good. And if you want to see how to set up a packet filter, well, there's still my book around, which is this. Still have it. But let's face it, it's from 2006, and at that time Linux couldn't do any connection tracking at all. So things have changed since, but it might give you a couple ideas how to approach these things. Okay. If you want to get really to the absolutely fundamental details, There's the list from the Internet Assigned Numbers Authority, which I've mentioned before. And there are the individual RFCs, the request for comments from the Internet Engineering Task Force, the official specifications. Okay, so much about ICMP filtering. Hope you enjoyed it. Hope you found it useful. If you did, or if you don't agree with it at all, come over to the forum at www.stepladder-it.com/bivblog/33. Always looking for discussions there. Every once in a while somebody shows up. And in any case, hopefully see you again soon. Bye.